Chapter 1 of Chemical Structure and Reactivity. So I'm Brown Nugget, and I've been a member of CODS since last year. The reason why I mainly joined CODS is to prep myself for the US National Chemistry Olympiad. I actually started prepping for it when I was in 8th grade. The first thing I did was I opened up an OpenStax textbook, threw myself into thermochemistry with no prerequisites. So later on, in my school we had like a summer bridge program. They took our group to this chemistry lecture. So that really ignited my love for chemistry. Shout out to Kuravax for actually recommending me this textbook when I was starting off. This textbook is meant for first year undergrad students, so it's meant to be accessible. So this book actually likes to go like deep into the fundamentals and build off quickly from there. So a lot of this may sound easy to y'all, but some of it will be heavily built upon, so that's why I'm just covering these fundamentals. So let's start off with covalent bonding. So, if you've taken normal chemistry before, you know that atoms strive to achieve an octet state, which is where their electron subshells, which will be discussed next lecture, are completely filled. And it is a universal law that everything, I repeat, everything wants to get to a lower state of energy. What covalent bonding is just the sharing of electrons between elements. So that's in order to achieve an octet state. Now, what we use to describe covalent bonding in simple molecules are known as Lewis structures, and they represent the valency, the valence electrons in each element. For example, oxygen has 6 valence electrons, hydrogen has only 1, etc. So, of course, there are going to be 2 electrons in every bonding and lone pair. So what a bonding pair is basically the 2 electrons that are shared in atoms, and a lone pair does not participate in bonding at all. That's mainly simple. Now, let's move on to what formal charges are. Assuming that you've drawn like some simple Lewis structures, let me refer back to H2O Lewis structure. Now, the formal charge on an atom is calculated as the number of valence electrons in an atom minus 1 for every bonding pair and minus 2 for every lone pair. Now, let's just think of this like logically, okay? So we all know that bonding pairs and lone pairs have 2 electrons each. Lone pairs do not participate in bonding, which means they're quote-unquote localized to a single atom. And that's why you do minus 2 for every lone pair. Now for a bonding pair, there will of course be 1 electron contributed from first atom and 1 electron contributed from the second atom. Double bonds have 4 electrons and triple bonds have 6 electrons. So but you can just think of double bonds right here. For now, it's just like 2 single bonds in this sense of like formal charges. So for example, in this hydronium ion, oxygen has 6 valence electrons. And you can see it has 3 bonding pairs, to the hydrogens right here. And also has 1 lone pair. So 6 minus 3 minus 2 is of course plus 1, which means that the oxygen carries a formal charge of plus 1, as seen in this example. And for something like the nitrate ion, just work through the formal charges for every single one of these. So let's start off with this oxygen. This oxygen has 2 bonds and 2 lone pairs. So oxygen has 6 valence electrons. So that's 6. Minus 2 because of this double bond right here. And minus 4 because of these 2 lone pairs. So the formal charge on this will be 0. For this nitrogen atom, there are 4 bonds to it, and we all know that nitrogen has 5 valence electrons, so this nitrogen atom will carry plus 1 formal charge. And for these 2 oxygen atoms, these oxygen atoms are the exact same. Oxygen has 6 valence electrons, and it has 3 lone pairs and 1 bond. So it's going to be 6 minus 1 minus 6. The minus 1 is contributed by the single bond right here. That will give these 2 oxygens a minus 1 formal charge. Now, here's the first exercise for y'all. Right here's the cyanide ion, and for each atom in this molecule, try assigning a formal charge and show you're working. So right here, the answer to exercise number 1. So carbon has 4 valence electrons. As seen in the periodic table, it has a triple bond right here and a lone pair. So that'd be 4 minus 3. The reason why I put minus 3 is because the triple bond right here, and minus 2 because the single lone pair right here. So this carbon would carry negative 1 formal charge. Nitrogen also has the triple bond and a lone pair. So that would be 5 minus 3 because the triple bond and -2 because of this singular lone. That's mainly it. So let's go on to talk about resonance. Now, assuming that we've all learned about Lewis structures, sometimes for molecules, you can draft multiple Lewis structures, which can cause some confusion at times. Now, what we can do is we can draw something known as resonance. It basically shows all the possible Lewis structures that can contribute to how electrons are shared within a molecule. If you look at a molecule of this is known as formaldehyde or methanol, and try to observe it, even though you can't, that does not mean that the molecule can flip-flop between these forms. It does not just randomly switch. What resonance basically states, is that the true way that how electrons are shared within a molecule is represented by a mix of these resonance forms. Usually, when we're looking at resonance structure, the one that appears the cleanest, aka maybe the one that just simply appears to have the least formal charges, usually contributes a lot, if not the most. Since oxygen is a lot more electronegative than carbon, having a negative formal charge on that oxygen would mean that structure C would contribute more than structure A. Because think about this. Since oxygen and carbon in a bond, it's a big electronegativity difference, that will cause the electrons to be somewhat skewed side of the oxygen. So a negative formal charge would be most appropriate for the situation, and overall structure C would contribute more than structure A. So let's move on to oxidation states. So oxidation states will be heavily mentioned once we get into electrochemistry. So if you have a molecule, the sum of all oxidation states times the number of atoms that have a certain oxidation state is equal to the overall charge in the molecule. Now I'll just show y'all more so a practical example. So we have the nitrate ion, NO3, and I also obtained this table showing common oxidation states for elements. So in NO3, we know that hydrogen usually has a -2 oxidation state, and the only exception is peroxide and F2O. Now, this is not a peroxide or F2O, so this means that oxygen automatically has a -2 oxidation state. We can set up the small equation, and since the overall charge of this NO3 minus molecule was -1, we can set up this equation so that x plus 3y equals -1, where x is the oxidation state of nitrogen and y is oxygen. Now this has a coefficient of 3 because there are 3 oxygen atoms in this molecule. So substituting -2 for y, and through some simple algebra, aka adding 6 to both sides, the oxidation state of oxygen is -2, and for nitrogen it's +5. So that's mainly what oxidation states are. Now right here, we're introducing what's known as VSEPR. Most of the times in chemistry, finding out how atoms are bonded within a molecule can be super crucial. So VSEPR basically states that electron pairs, whether they're bonding or lone pairs, always try to get the most space because like charges repel. So you can see these two electron pairs, telling each other to get away. And the second postulate is that lone pairs try to occupy more space than bonding pairs. This is mainly because bonding pairs are between two atoms and lone pairs just kind of sit on their own, which means that they'll try to occupy more space. Now, VSEPR just uses these postulates in order to predict the shape of a molecule around a central atom. Now, unfortunately, VSEPR is a bunch of memorization, so what I advise is going on to Quizlet or Anki, getting some flashcards, and try to memorize these VSEPR tables. I suggest using something like Active Recall. Now, VSEPR has its limitations. Because it is a purely theoretical model, it's not actually going to work for some cases in the real world. So what we can do is we use X-ray crystallography to get the shape of molecules in a crystal. This is more so an empirical approach on where atoms are placed in a molecule. So right here's a video. This is from my good friends at the Protein Data Bank channel. So this video mainly uses proteins as an example for X-ray crystallography, but in practice this can be used for any molecule that can be found in a crystal form. So going on, we'll talk about the types of bonding. So of course we have covalent bonding, which is just the sharing of electrons between atoms. Now we'll go on to ionic bonding. So covalent bonding is the sharing of electrons, but ionic bonding is basically where one element gives up some of its electrons and another element manages to gain some electrons. So it's sort of like a win-lose situation. So for example, in magnesium oxide, MgO, magnesium has two valence electrons that it needs to achieve its octet state, and oxygen just needs two more electrons to reach its octet state. Basically, what the magnesium can do is it could just donate its two valence electrons to get its octet, and the oxygen can just receive the two electrons from the magnesium to achieve its octet. So it's a very fair trade. And rule of thumb for ionic bonding is that it happens between a metal and a non-metal. Metals have a great magnitude, less electronegativity than non-metals. So then, from ionic bonding, we move on to metallic bonding, which is surprisingly simple. All metallic bonding is if you have a metal, what will happen is that the electrons, instead of just being like localized to a single atom, it's kind of like a sea of electrons just inside the metal. Like a sea of electrons just flowing across a sea of nuclei. And this explains why metals can be malleable, which means that they can be, hit into thin sheets, why they're ductile, aka, drawn into wires. I'm pretty sure we know that copper is used for wire. And that's why metals also have a great luster or like a shine to them. So, for example, one of my favorite elements, palladium, is a silvery white metal, and metallic bonding perfectly explains how it can be hammered into these thin sheets, how it can be drawn out, and just overall it's great shine. So those are the three main types of bonding. Now, we've only talked about the forces that are between atoms in a molecule, but there are fundamental forces that are between molecules. So these forces are known as IMFs. They stand for intermolecular forces, which are between molecules. Intramolecular forces exist between the atoms in a molecule. So we're going up, one step. So the first kind of IMF that we want to know are London dispersion forces. And these were formulated back in like the 50s. And at that time, we have our good old friends, Albert Einstein and Schrodinger, and a bunch of other cool quantum physicists that came up with the notion that, hey, electrons are not actually particles. They're actually waves, and they have probability densities to them. And these probability densities will be discussed later on in the next lecture. But because they have probability densities, electron density across an atom is uneven, which means that one side of an atom can become randomly positively charged, and another side of an atom can become randomly negatively charged. So this will create a short momentary amount of attraction between these two atoms. Now, of course, I'm just using atoms as an example here, but you can also extend this to molecules. What polarizability refers to is probability of electron distribution. Basically, can be more so skewed or just like distorted. So generally, something like chlorine would be more polarizable than fluorine. If you refer to a periodic table online, chlorine is period lower than fluorine, which means that its electron probability densities reach out further, which means that it can be distorted to a greater extent. Now, let's move on to the next one. Dipole-dipole forces are created from a difference in electronegativity that skews electrons towards a certain element, and this will lead to partial positive and negative charges. And because of this, we gain increased interaction and attraction between molecules. And then we move on to hydrogen bonding. You can think of it as somewhat of a more extreme version of dipole-dipole. It happens when hydrogen is bonded to fluorine, nitrogen, or oxygen. For back to this example, we have water right here. You can see we have the hydrogens bonded to the oxygen. So this will have hydrogen bonding. That's why something like water, like especially when I'm making pasta, that's why water usually takes something like, a solid 5 minutes to get to its boiling point in my experiences. That's because of these hydrogen bonding forces between water molecules. So here's a statement from my chemistry teacher. So taking all of these IMFs into account, matter is fundamentally attracted to other matter. So now let's move on to solids. So there are four main types of solids that you need to know: molecular, covalent network, metallic, and ionic. So let's start off with molecular solids. What molecular solids are is basically they are solids that consist of discrete, aka, separate molecules. So for example, pure iodine is a solid. And if you manage to, cut a slice through it and see the positions of the iodine molecules, we have a technique for that, X-ray crystallography. We can see that there are sort of like small clusters of these iodine molecules. So that's what a molecular solid is. Now, we can extend this notion into covalent network solids. For example, silicon dioxide. You experiment with silicon dioxide every day. Your windows are made out of silicon dioxide. And what silicon dioxide has is that it has covalent bonds that extend throughout the entire thing, through the entire solid. And what these covalent network solids have, because of this extended bonding throughout the entire solid, is that it'll just have like a higher melting point. It's more resistant to heat change. And metallic and ionic solids, those basically build off our types of bonding. Ionic bonding, giving up, gaining electrons. And metallic bonding, just a sea of electrons and a sea of nuclei. Say for now, we're past the hard part. We focused on solids. Let's focus on the other end of the spectrum of states of matter. So let's talk about the ideal gas law. So in my opinion, it's super crucial to chemistry, but it's arguably like one of the most fun laws to use. So what ideal gas law asserts is that the pressure of a gas times the volume of the container that the gas is in is equal to the moles of the gas times R. Now, what R is basically it's referred to as the universal gas constant, and is either measured in kilopascals or atmospheres. Now, kilopascals and atmospheres are two units of pressure that are used in chemistry. Usually, in chemistry, you would use something like atmospheres more often than kilopascals from what I've seen. So, the value for R in this scenario for measuring it in atmospheres is 0.0821. So for the second example, what is the pressure of 1 mole of helium gas kept in a 5-liter container? The answer, using some simple algebra, we can see that P is actually equal to nRT over V. Because if we're dividing both sides by V, we isolate the P variable on our own. So that's the answer for example 2. Now, what we've gone over so far, of course, the fundamentals of this book, covalent bonding, formal charges, resonance, oxidation states, VSEPR, and right here we have the big VSEPR table, X-ray crystallography, which is more experimental than VSEPR, kinds of bonding, intermolecular forces, solids, and the ideal gas law. So that's mainly it, honestly. So you can contact me at Brown Nugget on Discord to give your feedback, or you can just contact Ayame.